in this video we're going to be looking at topic 4B, crude oil, and we're going to be focusing on the double content. And this is part of the IGCSE chemistry course from Edexcel. So we're going to be looking at what crude oil is and how we can separate it using fractional distillation. We should know the names, the uses and the trends of these fractions. We should also be able to understand the products of combustion and why complete combustion and incomplete combustion are different, and the problems with incomplete combustion. We'll also be looking at how we can form sulfur dioxide and nitrogen oxides due to the impurities in fossil fuels and the effect that this can have on the environment. And we'll also look at cracking and how we can convert long chain alkanes into short chain hydrocarbons that are a little bit more useful for us. So first of all, let's start off with what crude oil is. Well, crude oil is a mixture of hydrocarbons, and it's got lots of different chain lengths. We can have carbon chain lengths from 1 carbon up to over 100. And this is a very dark, sticky mixture, and it is not particularly useful when it is in its natural form. It is a finite, non-renewable source, and we cannot replace it in our human lifespan. And we know it as one of the fossil fuels, meaning that it is made from the remains of ancient marine life. And as you learned in Key Stage 3, of course, fossil fuels are not renewable. We will run out of them in our lifetime. So it's about trying to find ways to replace these fossil fuels. But what we're going to focus on is the chemistry of it and how we currently use crude oil. So what we know about the different hydrocarbons is that as we increase the chain length, we see specific trends. And these will be mentioned when we look at the alkanes and the alkenes as well, but it is trends that you should know and be able to give some information about. So what we see as we increase the chain length, first of all, is we see the boiling point increasing. And this is to do with the intermolecular forces between the different molecules. You will touch on this more when you get to A level, but the general gist is that as the molecule gets larger, it has more intermolecular forces which are tougher to break. Therefore, our boiling point is increasing because we need more energy to overcome these forces. We also see that the liquids become less volatile, meaning they don't evaporate easily, and to the point where eventually they become solids which can't evaporate. Then we also have the liquids becoming more viscous. So this is about how easily they flow. So if you were to compare, for example, water and honey, water is not particularly viscous because it flows quite easily, whereas honey has a higher viscosity because it doesn't flow or pour as easily as something like water. We also see that the liquids become darker in colour, and we have our flammability decreasing, meaning they don't catch fire as easily. And as I said, all of these properties are all linked into the intermolecular forces increasing as the carbon chain length increases. So crude oil itself has no actual uses. The black sticky substance is not what we actually use in our everyday life. What we have to do is we have to separate the crude oil, because remember, it is a mixture and we want to separate it into specific hydrocarbons, and we call these fractions. And the fractions are a mixture of different carbon chain lengths, but they all have similar boiling points. So we're taking advantage of this physical property of a boiling point and being able to then separate out the crude oil. And this process is known as fractional distillation. Now this link here is from the Fuse School, and it is a very good link to clearly explain fractional distillation, and you can find that in the description below. So this is what we have a fractional distillation happening, and this is known as the fractionating column. And you can see that we have a temperature gradient. So we start at cool temperatures up at the top at about 25 degrees, and then it gets hot as you get to the bottom at about 350 degrees. So what happens is the crude oil is heated or is vaporized in order to become a gas, and it is then passed into the fractionating column. And depending on the boiling point, the particles of the hydrocarbon are going to rise or are going to fall into the different parts of the fractionating column, and once they get to their boiling point and they can condense, they are then collected in these trays. So this is where the condensed hydrocarbons are collected, and then they are removed from the fractionating column. And you can see that we have a number of different fractions that we can split this crude oil into, and there are 6 that you have to know. So the first one is refinery gases. Then we have gasoline or petrol. Now naphtha is another fraction but is not part of the IGCSE, so you're not required to know that one. Then we have kerosene, diesel oil, fuel oil, and residue, or sometimes known as bitumen. So we can have 2 different names for that last one. And what we see is this trend. So our small molecules that come out at the top of the refinery gases, they have a low boiling point, they're very volatile, they're going to flow particularly easily because they are gases, and they're going to catch fire very easily. The large molecules down the bottom, like in the residue, are a high boiling point, to the point where they're almost solid. They are not particularly volatile, so they don't evaporate easily. They do not flow easily, and they do not ignite easily either. So just to summarise, we had our crude oil being heated until it boils. The vapours pass into the fractionating column, which has this temperature gradient, and depending on its boiling point, the hydrocarbon will travel up the column and will condense at different levels, and then they are collected. So we are using this boiling point in order to get our separation. And what you have to know are the names of the fractions and their uses. So we're going to start off with refinery gases. So these are between 1 and 4 carbons, and they have a boiling point below 30 degrees. So obviously we want to keep them below room temperature to make sure that they're gases. And we tend to use these for domestic heating or for cooking. If you've ever been camping, you may have used a small butane-based cooker in order to cook any food, and it tends to be this one of these refinery gases, usually butane or sometimes propane. Then we have petrol, and this is the one that most people are most common with because we use it as a fuel in our cars. They tend to have between 7 and 9 carbons. Most commonly they have 8 carbons. They're usually based on octane, and they have a boiling point between 100 and 150. Then we move on to kerosene, which has between 11 and 16 carbons, and much higher boiling point. Now we're getting up to the 200 or 300s, and this is used for fuels for jet aircrafts and also for heating oil for small lamps. So you may have heard of a kerosene lamp that burns this as a fuel to give off heat and light. Then we move on to another fraction that you've probably heard of, which is diesel, and this can have between 11 and 21 carbons, and again, similar sort of boiling point to kerosene, but just slightly different. This tends to be used for fuels for large vehicles. For example, buses, lorries, cars, or things with large engines. Then we move on to fuel oil, which has between 20 and 27 carbons. Now we're moving up to about 350 to 450 degrees. And this tends to be used as a fuel for ship or marine vehicles, or we can use it for industrial heating. And then lastly is bitumen, or sometimes known as residue. And this has above 35 carbons and has a boiling point above 500, so this tends to be fairly solid, and this is most commonly used for road surfaces. You may know it as tar when we add in different things, but that surface that we use to make roads is based from bitumen, which we get from crude oil. So those are the different fractions that we find in fractional distillation. As I said, you have to know the names and at least one use for each of the fractions. This is a common exam question. So now we're going to talk about the combustion of hydrocarbons, and this was mentioned back in topic 4A, but just as a reminder, we have a fuel which when we burn it is going to release heat energy, and the burning of these fuels is known as combustion. And there are 2 types of combustion. There is complete combustion and incomplete combustion. So complete combustion is when we have excess oxygen, or a plentiful supply of oxygen, meaning we can fully burn each part of the hydrocarbon. And this time we're going to form carbon dioxide and water. So we can write out a full balanced chemical equation for this as expected at GCSE, along with our state symbols. So we can have methane, which is CH4, plus oxygen, which is O2, and both of these, of course, are gases. We're going to make carbon dioxide, which is a gas, plus water, which is a liquid. Now, when we're balancing hydrocarbon equations, these are probably some of the easier ones to balance. We want to do the carbons, then the hydrogens, and then add up the oxygens in the products and divide it by 2, and that will give us our answer. So the carbons, first of all, we have 1 on the left and 1 on the right, so they are balanced. For the hydrogens, I have 4 on the left and only 2 on the right, so I need a coefficient of 2 in front of my water. Then I add up my number of oxygens on my right-hand side. So I have 2 from the carbon dioxide and 2 from the water, giving me 4. I divide that by 2, and I get an answer for a coefficient of 2 for the oxygen. And that's my complete combustion of methane. Now, the second type of combustion is incomplete combustion, and this is when we have a lack of oxygen, or we don't have the oxygen in excess, meaning we don't have enough in order to fully burn the hydrocarbon. So this time we're going to form carbon monoxide and the water. So again, we should be able to write out a full balanced chemical equation with state symbols for this. So if we have our CH4 as a gas, reacting with the oxygen, remember O2 is diatomic, and we're going to form carbon monoxide, so this time CO, but it is still a gas, and we still make the water, which is H2O. Now, of course, we have to balance it. So my carbons, I have 1 on the left and 1 on the right, so that is balanced. The hydrogens, I have 4 on the left, but I only have 2 on the right. So I'm going to put a 2 in front of the water. And now, again, I add up my number of oxygens and divide it by 2. So I have 1 oxygen from the carbon monoxide, 2 from the water, giving me a total of 3. I can divide that and get 1.5. Now, you can use fractions for diatomic molecules. If you can't remember how to balance using the fractions, you might want to go back and have a look at the video on balancing equations. That might help jog your memory. But for diatomics, you can have a fraction of a half, but you cannot have anything other than that. Or if you wanted to, you could multiply everything by 2, which would give you 2 CH4s plus 3 O2s to give you 2 carbon monoxides and 4 waters. Okay, if you notice, the ratios are still the same. The only difference is this time we have whole numbers. So that is a perfectly acceptable answer. As long as your ratios are correct, then your answer will be just fine. Now, carbon monoxide is a real problem in the fact that it is a poisonous gas. And the reason for that is it actually reduces the body's ability in order to carry oxygen. And it does this by bonding with the hemoglobin that we find in our red blood cells. And when it bonds to the hemoglobin, it stops the oxygen from bonding to it. So then it can stop the oxygen getting to your cells and be an issue with respiration. So it actually can be toxic and can be fatal if you inhale too much carbon monoxide. So it's really important that we don't have a lot of incomplete combustion happening because we don't want to be releasing this toxic gas. Now, burning hydrocarbons does form carbon dioxide, which is a greenhouse gas, and you discussed greenhouse gases back in topic 2C, gases in the atmosphere. And greenhouse gases are used to trap heat that is radiated from the Earth's surface, and this can lead to climate change. Now, this is a problem because we don't want climate change to happen. It has an effect on our environment and has an effect on the weather and the temperature of the Earth, and of course it's not good for the Earth. So we want to try and avoid burning hydrocarbons to make this carbon dioxide, which is why we're always trying to look for more efficient fuels that can give us just as much energy but not as much pollution. Now, acid rain is a side effect of burning these hydrocarbons. So rain is naturally slightly acidic, around about 5.6 pH. But when the pH falls below this, we call it acid rain. And acid rain is formed when water and oxygen in the atmosphere react with sulfur to make sulfur dioxide, or nitrogen to make nitrogen dioxide, and these impurities are found in the fossil fuels. So we have sulfur or nitrogen impurities in the fossil fuels, and when these are burned, we form sulfur dioxide and the oxides of nitrogen, and when they react with water, we form sulfuric or nitric acid, and that causes the rain that we get to fall as acid rain. So just a few examples to show how this works in terms of equations. You have the sulfur burning with the oxygen to form SO2. That can react with the water to form H2SO4, which is sulfuric acid. Or if it only reacts with 1 mole of water, then we make H2SO3, which is sulfurous acid, but still just as dangerous in terms of acid rain. When we have the nitrogen, it burns to form nitrogen monoxide. Now we can get other oxides, but we're going to stick with the easy one. And that nitrogen monoxide can further react with the oxygen and water in the atmosphere, and it makes nitric acid. Now, acid rain is not something that you go outside and it falls on you and it burns your skin. The acidity is not as strong in order to be able to do that. It is fairly diluted. However, it does have negative effects on our environment or on our ecosystem. So acid rain can be damaging to marine life, can cause it to be either harmful or even fatal to specific marine life. It kills plants and trees, which then has an effect on our delicate balance that we have with plants and trees in terms of photosynthesis and respiration. It can also corrode limestone buildings. So any buildings made out of a rock called limestone can be corroded away, and then that could cause damage to the buildings. It could also cause some metals to corrode. So if you've got cars or bridges or any metal structure can be affected by consistent acid rain. One of the most common countries that has an issue with acid rain is China, because they do have a lot of fossil fuels, and so do the US and the UK as well. And because they're burning a lot of these fossil fuels, they're constantly giving off these impurities, and it does cause acid rain in the atmosphere. So we can have these negative effects showing in these countries that burn a lot of fossil fuels. Now, when we look at the fractions that we get from fractional distillation of crude oil, what we see is the majority of them are used as fuels. Gasoline being used for cars, diesel being used for larger vehicles. And whilst they are useful as fuels, what we find is that some fractions are much more desirable than others, meaning they have a higher demand. And what we need to make sure is that when we are undergoing fractional distillation, that we are keeping up with that demand. So the more desirable fractions have not only more uses, but then they become more profitable. So what we have to do is, as chemists, is to take the least desirable fractions, so the ones that we don't get a lot of profit from or that we are not going to be able to use particularly well, and then transform them into the most desirable fractions. And the way that we do this is by something called cracking. So you can see here that when we look at fractional distillation, the majority of our crude oil is used as gasoline. Over 43% is used as gasoline and 23% for diesel. So we're looking at 66%, 2/3 being used as fuels for vehicles. So that's a very high demand that we have in terms of the crude oil. So we need to make sure that we are balancing this with what we're actually making. So cracking is a process in which long chain alkanes are converted into alkenes or shorter chain alkanes. So the whole point is to take these long, undesirable substances and make them into shorter, more desirable fractions. Now what we can do is we can write out an equation to show this, and the easiest way to have a cracking equation is to figure out how many carbons and how many hydrogens we have on both sides. And a typical exam question will ask you to complete an equation. So they'll give you the reactants and the potential products, and they'll take one of the products out and ask you to work it out. And I'll show you an example in just a minute. What we find is that we are going to form at least one unsaturated alkene with double bonds because there are insufficient hydrogen atoms to form two alkanes. So if we have one substance breaking down into two shorter chains, one of them will be an alkane and one of them will be an alkene. If we have more than two, what we'll find is that, again, only one is an alkane and the rest are all alkenes because we don't have enough hydrogen in order to fully break it down. So let's have a look at an example. So if we use the example of C13H28. Now this hydrocarbon is a liquid. It is quite a long chain, but it's not entirely useful to us. So what we want to do is break it down into more useful fractions or more useful molecules. Now the problem with cracking is we cannot identify exactly how the molecule is going to break down. All we're doing is breaking the bonds between the carbon atoms, so we cannot predict that, meaning you can get lots of different reactions happening in this process. But that's okay, as long as you can identify at least one possible reaction, then that would be a suitable answer in an exam. So for example, I could break this down into a C2H4. I could have a C3H6. I could have another C2H4, so we'll put a 2 in front of that, and I could also make a C6H14. What you'll notice is that the number of carbons and hydrogens is the same. So if I have 13 carbons on the left, I must have 13 carbons on the right, 28 hydrogens on the left, 28 hydrogens on the right. And I'm making an alkene, an alkene, and an alkane. So you can see that we've got this mixture. But we don't necessarily know that's how this is going to break down. I could start with my same C13H28, break it down into 2 C2H4 again, but instead of making the C3 and the C6, potentially that doesn't break and I keep the C9H20. Still have my alkene and my alkane. Both of these are perfectly acceptable cracking experiments. We cannot predict which one is actually going to take place. So what we do with cracking is we break the molecule and then we would test what's being formed to identify them and then use them appropriately. Now, some cracking reactions can even produce a small amount of free hydrogen. So again, if I keep my C13H28, I could break that down again into my 2 molecules of ethene, C2H4, which is my alkene. I could make the C3H6 and a C6, and instead of C6H14, I might make C6H12, meaning I've made 3 alkenes. And that would cause me to have 2 hydrogens left overall. So my mixture that I make from my cracking experiment will either be a mixture of alkenes with 1 alkane, or if it's all alkenes, we will form some hydrogen. Now, a typical question for this, as I said, they may give you the C13H28 and they would give you 2 out of the 3 products and ask you to identify the third. And it is as simple as seeing what the difference in the number of carbons and hydrogens are on both sides. So you can figure out how many carbons you have and subtract that from how many you should have. And that would tell you what the missing product is. And during the cracking process, the fuel oil or the long chain hydrocarbon is heated in order to vaporize it, and then it's passed over a catalyst. And the catalyst tends to be silicon dioxide or silica, or aluminium oxide, also known as alumina. Sometimes they can also use something known as zeolite, which is a mixture of the alumina and the silica. Any one of those would be a suitable answer. And they are also at 600 to 700 degrees Celsius. These are conditions that you have to know. This is sometimes known as catalytic cracking or even thermal catalytic cracking. So the thermal being the heat at 600 to 700, the catalytic being the use of the catalyst, and then the cracking breaking down the molecule. And oil companies will carry this out to most commonly produce more petrol or gasoline, or to make alkenes that can be used to form polymers. And we'll discuss polymers in topic 4H. And we can carry out cracking in the lab, and this is the setup that we use in order to do it. So we have our mineral wool soaked in liquid paraffin. So this is our hydrocarbon that we're going to crack. And we soak it in the mineral wool to keep it in place at the end of the test tube. We then have our porcelain chips, which is either the silica or the alumina, and then that is underneath a Bunsen burner that we use in order to heat the catalyst. Now what happens is you heat the catalyst and you heat the mineral wool with the liquid paraffin on and off. So you alternate between the two, but you spend more time heating the catalyst because the paraffin, of course, is very flammable and we don't want it to combust. All we want it to do is to be vaporized and turn into a gas, so that when it turns to a gas, it travels over the catalyst and is then broken and then travels down through the delivery tube. And typically we're going to be collecting the gas that is formed. And most of the time when you do this in the lab, you're collecting ethene gas. And you can test the ethene to prove that it is an unsaturated molecule, and we will talk more about this when we do the alkenes in topic 4D. But this process is how we carry out cracking in the lab. So a couple of key points. As I said, the mineral wool is used to hold the paraffin in place, and it makes sure that we're not heating the alcohol or heating the hydrocarbon directly, because we want it to slowly react with the catalyst. The most important part of this experiment is avoiding something known as suckback. Now, this happens after we have heated the test tube. When we heat the test tube, we're going to get an expansion of the glass and the delivery tube. And if we then just remove the heat, then the delivery tube and the test tube is going to contract, which could cause water to be sucked up the delivery tube and go right back into the hot test tube. And if that happens, the test tube can shatter. And we, of course, want to avoid that because that's a very dangerous situation. So what we do when we're carrying out a cracking experiment is, before we take away the Bunsen and take away the heat source, we actually remove the delivery tube from the water, so that when we turn off the Bunsen and then the whole setup begins to contract, it is not sucking up any of the water to go into the test tube, and we're not getting any sort of dangerous situation. So we're going to finish off by looking at some past paper questions. Now, there are quite a few that we'll go through at the different parts of a crude oil question, and these can all potentially be in one long answer question that could be worth up between 12 and 15 marks. So it's a very good idea to make sure that you're confident in all the different sections of crude oil, and then we'll start to tie everything together when we look at organic chemistry in a bit more detail. So the diagram shows a typical fractionating column that's used to separate crude oil into fractions. And we want to name the first fraction and the bottom fraction. So fraction A, we know, is the refinery gases. So as I said, remember, you have to know the names and also the order of the fractions. And the one that comes off at the bottom is our bitumen. And that's our 2 marks. For the second part, most compounds in crude oil are hydrocarbons. We want to state the meaning of this. Now, we did talk about this back in topic 4A. It is a typical exam question. It's a 2 marker, and we always answer it in exactly the same way. They are compounds made of carbon and hydrogen, and that keyword only. You get a mark for specifying that they are only made of hydrogen and carbon. So always make sure to put that. And then we want to describe how the boiling point, the colour and the viscosity of the fuel oil fraction differ from that from the gasoline. So if we go back, we can see we're comparing fuel oil and the gasoline. So it doesn't matter which way you want to explain it, but we're going to explain it in terms of the fuel oil comparing back to the gasoline. So there are three things that we can say here. The fuel oil is going to have a higher boiling point. The fuel oil is going to be darker. And the fuel oil is also going to have a higher viscosity. Or you could even say it flows less easily. Something like that, just to show that we've got a difference in how easily they flow. And we're always looking for boiling point, the colour and the viscosity from the question, and just specifying what is actually happening. So increasing our boiling point, getting darker, and they're flowing less easily. So now we're looking at the fact that some of the fractions can be catalytically cracked, and the general equation for this is that we start with an alkane, which is our long chain, and we make a shorter chain alkane and an alkene. So the two conditions that are used in catalytic cracking is always looking for what is the catalyst and what is the temperature. And it doesn't matter which order you put them in. So we're going to start with the catalyst. So we have a silica or alumina catalyst. And the temperature is between 600 and 700 degrees Celsius. They will accept a value, so if you wrote 650, that would be accepted, but you should always try and give the full range. So if you remember 600 to 700, that would then get you the mark. And the chemical equation for one cracking reaction is C6H34, giving you C8H18, two C3H6s, and compound Q. And we want to deduce the formula of compound Q. So the first thing I'm going to do is I'm going to look at the right-hand side of the molecule, and I'm going to count my carbons and my hydrogens. So I've got 8 carbons plus 2 times 3 is 6, giving me 14. Then I have 18 hydrogens plus 2 times 6 is 12, so 18 plus 12 is 30. And then my left-hand side, I know is 16 and 34. So now to work out compound Q, I just subtract them. So for the carbons, I have got 14 and I should have 16. So I need 2. And for the hydrogens, I've got 30 and I need 34. So that must be C2H4. And notice I have to put the molecular formula, not the name or any other type of formula. So when hydrocarbons undergo incomplete combustion, a poisonous gas can be formed. We first of all want to state the condition that causes the incomplete combustion, and this is insufficient or lack of oxygen. Okay, you could also say that the oxygen is not in excess, but you cannot say no oxygen, because we do still have some oxygen in order for the combustion to happen, we just don't have enough. And we want to identify the poisonous gas, so that is carbon monoxide. We can either identify by the name or even the formula, and then explain why this gas is poisonous. It decreases the capacity of blood to carry oxygen. So in biology, you'll probably go into a bit more detail about the fact that it's going to form carboxyhemoglobin when the CO bonds with the hemoglobin, but in chemistry, we just look for a very simple answer, that it decreases the blood's ability to carry oxygen around the body, or stops blood cells from carrying oxygen. Something even as simple as that. And then another problem with using hydrocarbon fuels is the formation of a substance that can cause an environmental problem. And we can see the sequence of equations, and we want to name the product in each of these. So we have SO2, that is sulfur dioxide. We then have SO3, which is sulfur trioxide. Remember, if you're not very good with the formulas or naming, you might want to go back and have a look at topic 1E. That can help you with that. And then H2SO4 is sulfuric acid. And you get 2 marks for getting the gases is the first mark, and then the sulfuric acid is the second. And then describe one environmental problem caused by the H2SO4 formed. So for 2 marks, I want to name it and then give an example of what happens. So the environmental problem is acid rain. And then there are a number of different things that you could say here. We're just going to keep it very simple and say that marine life is killed or damaged. You could talk about the fact that we've got plants or trees being damaged, or their growth is stunted, anything like that, or even that limestone can be corroded or eaten away, anything like that. Any one clear issue with acid rain would get you that second mark. And there we can see the answers to the past paper. So there's the first set and then the second set. Now that's everything for topic 4B, crude oil, for the double content. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel.